This is a bonus video for those of you who wanted to see why we have the type of power function that we do that causes the number of unrooted trees to increase so quickly as we go up in number of species. All right, so let's remind ourselves first about the equation that we're working with, and then we'll see how this equation actually comes to be when we're working with the actual trees. So it's a power function, so it's like a summation series, except we're going to multiply the terms. We start with I equal to 3, going up to the number of species, and the equation for each term is 2 times I minus 5. So the simplest case is if the number of species equals 3. And so if we were to plug 3 into this equation, then what we would end up with is this term here being equal to 6. 6 minus 5 is 1. And that says that there's one unrooted tree, one unique unrooted tree when you have 3 species. And that's easy to see because there's only one way to draw a 3-species unrooted tree. I defy you to find any other way to do this than the way I'm doing it right now. And so that is our one unrooted tree for 3 species. Now if we have 4 species, we already have the term 1. We're going to add one more term where I equals 4, and 2 times 4 is 8, minus 5 is 3, and this, so we have our 2 terms, 1 and 3, and so there are 3 unrooted 4 taxon trees. Now let's see if we can understand that by looking back here at the 3 taxon tree that we've got right here. With this 3 taxon tree, there are 3 informative, unique ways that we could add a 4th species. And basically, each branch is a place that we could add a 4th species. So for example, we could add a 4th species here, we could add a 4th species here, or we could add a 4th species here, giving us 3 different places that we could put that 4th species on there. And if we were to draw each one of these out, then we would have the following set of unrooted 4 species or 4 taxon trees. A, B, C, D. This corresponds to this option here. Okay, so if we add D here, then we would get this option over here. Another way that we can do it is the following. A, C, B, D. So that's when B and D are next to each other. And that's going to correspond to this option here. And then finally, the only option that we haven't done yet is going to look like this, where we have A, D, B, and C, and that of course is going to correspond to the final option over here. And so we get our 3 4-species or 4 taxon trees. All right, so before we move on, let me erase the 3 taxon tree just to clean this up a little bit. All right, so what are we going to do now? Remember, we have our power series, which for 4 species have the terms 1 and 3. What's the next term going to be? Well, basically what we want to know is how many different ways can we add a 5th species to our 3 4 taxon trees? And because there are 5 branches in each tree, there are going to be 5 different ways that we can add that 5th species to each of the 3 trees. So this term here becomes a 5. And so we multiply all this out and we have 15 different 5 taxon trees. Each of the 5 taxon trees, each of those 15 5 taxon trees will now have 7 branches. So if we want to go up to 6 species, we're going to have 15 different trees, each with 7 tacks on it. And so we would go to the next step in our power series. Here, we add the 7 for the 7 branches, and this would be 105. So what we have here is the odd-numbered power series, 1, 3, 5, 7, and so forth. And the reason that it grows so fast is because each time we add another species onto it, we add 2 more branches to each tree. And so that's why we're getting this power series. So we start here with 1 3-taxon tree. There are 3 branches to which we can add, and so that's where the 3 comes from. Then each of those 3 have 5 branches, so we can add to that for our 5-taxon tree, and so forth as we go along. And that would take us up to the next one where we would have 7 branches.